Hello there, and welcome back to the Sleep Science. You're standing on a cold, rust-colored plain, the sky above you a butterscotch haze, thin and brittle like old parchment. The horizon curves gently, and in the distance Olympus Mons rises so wide it barely looks like a mountain at all. More like the edge of a forgotten continent. The air is thin. So thin, in fact, that you probably won't survive this without a pressure suit and a very optimistic attitude. Mars is not known for hospitality. And yet tonight, Mars is not the only visitor in this quiet neighborhood. High above you, beyond the faint whisper of dust devils crawling across the regolith, something glimmers. A shard of light, moving too quickly, too decisively to belong here. This is 3I/Atlas, an interstellar wanderer, a cosmic drifter that did not form in the comforting swirl of our sun's early disk but somewhere else entirely. Somewhere colder, stranger, older, perhaps. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, tell me where you're listening from and what your local time is. There's something wonderfully grounding about knowing where on Earth you are while we imagine standing somewhere else entirely. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tilt your helmet upward and watch 3I/Atlas glide against the faint starlight. The name itself carries weight. The I stands for interstellar, only the third confirmed object ever observed entering our solar system from beyond. The first, Oumuamua, was detected in 2017, tumbling mysteriously through our cosmic backyard. The second, 2I/Borisov, followed in 2019, clearly comet-like, shedding gas and dust as it passed. Each one rewrote textbooks in real time. And now this, 3I/Atlas, adds another chapter. The Atlas part comes from the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to scan the skies for potentially hazardous objects. A system originally built to protect Earth ends up spotting a traveler from another star. There's something poetic about that. Like installing a doorbell camera and accidentally catching a unicorn. From your Martian vantage point, the object appears small, just a brilliant speck, but its speed tells another story. It is moving far faster than most native comets bound to our sun. Its trajectory is hyperbolic, meaning it isn't looping around the sun in a cozy ellipse. It's diving in, curving briefly under solar gravity, and then leaving forever. No return ticket. No sentimental postcards. You imagine its journey before this moment. Drifting for millions, perhaps billions, of years in the interstellar dark. Between stars, space is unimaginably empty. If the solar system were the size of a coin, the nearest star would be thousands of kilometers away. 3I/Atlas has crossed that kind of desert. And now it slices through Mars' orbital neighborhood like a cosmic tourist who refuses to slow down for photos. Mars, meanwhile, has seen its fair share of visitors. The red planet bears scars from countless impacts, especially during the late heavy bombardment about 4 billion years ago, when the inner solar system was pelted with debris. That's a mainstream historical fact of planetary science. Mars' cratered highlands are a preserved museum of that violent era. Earth's evidence has mostly been erased by plate tectonics and erosion. Mars, lacking those restless geological processes, keeps its bruises on display. But this encounter feels different. Those ancient asteroids and comets were born in the same swirling nursery as Mars itself. 3I/Atlas was not. It carries chemistry forged around another star, perhaps a red dwarf, perhaps a sun brighter than ours. Spectroscopic observations, those delicate analyses of light wavelengths, hint at unusual ratios of volatiles. Maybe an excess of carbon monoxide. Maybe complex organic compounds clinging to its icy crust. You can almost see it now, a jagged nucleus tumbling slowly, sunlight igniting faint jets of gas as it warms. The jets act like tiny thrusters, subtly altering its path. Comets do this all the time. It's one reason predicting their trajectories can feel like trying to forecast the path of a cat chasing a laser pointer. Respectfully chaotic. And here's where things get interesting. Mars lies close to 3I/Atlas's projected path, not in direct danger, but near enough to make astronomers lean forward in their chairs. Orbital mechanics is a graceful dance of gravity and velocity. A few degrees of difference, a whisper of gravitational tug from the Sun, and the object could pass tens of millions of kilometers away, or much closer. Historians still argue whether early solar system bombardments delivered most of Mars' water or whether volcanic outgassing played the dominant role. The debate matters because if interstellar objects like 3I/Atlas can carry water and organics across stellar distances, then perhaps life's ingredients travel more freely than we once thought. Maybe planets aren't isolated kitchens. Maybe they share recipes. There's also the quirky tidbit that some researchers have half-jokingly suggested interstellar objects could act as natural seed ships, transporting microbial life between star systems, a concept known as panspermia. It sounds like science fiction, and it mostly is speculative, but the laws of physics don't forbid microbes from surviving inside rocks shielded from radiation. Tardigrades, those microscopic water bears, can survive vacuum and radiation that would make you dramatically reconsider your life choices. Still, you keep your expectations grounded. 3I/Atlas is most likely a chunk of ice and rock, shaped by collisions in a distant protoplanetary disk. Its approach to Mars is probably uneventful in cosmic terms. No fiery apocalypse. No alien monolith unfolding like an interstellar origami project. Just a close flyby. A whisper in gravitational language. But from where you stand, boots planted in red dust, it feels monumental. Because this is not just an object passing a planet. This is proof that planetary systems are porous. That the galaxy is not a collection of sealed snow globes but a dynamic, messy interchange of material. Stars fling debris outward. Other stars capture some of it. Over billions of years, the Milky Way becomes a grand recycler of worlds. 3I/Atlas is doing something simple and extraordinary at the same time. It is passing by Mars. That's it. No lasers. No secret mission briefing. Just gravity doing what gravity does. And yet, as it arcs across the Martian sky, brighter now, briefly, before it continues its long escape, you can't help but feel that Mars is being brushed by history. Not the history of one solar system, but of another. You keep watching. The dust settles. The sky remains thin and quiet. And the wanderer moves closer. The light grows steadier now, no longer just a fleeting glint but a defined presence against the salmon-colored sky. You track it as it slides westward, a silent bead on an invisible wire. 3I/Atlas did not begin its existence under this Sunday long before Mars ever cooled enough to grow a crust. Before Olympus Mons even dreamed of rising, this object was condensing out of dust around a completely different star. You imagine that alien nursery. A young star flickers in a dense molecular cloud, surrounded by a spinning disk of gas and debris. In our own solar system, this happened about 4.6 billion years ago, a mainstream historical fact in astronomy supported by radiometric dating of meteorites. Tiny grains stuck together, forming pebbles, then boulders, then planetesimals. Some became planets. Others remained leftovers, gravitational crumbs. 3I/Atlas was likely one of those crumbs, never promoted to planet status, forever stuck in cosmic middle management. But something dramatic must have happened. Interstellar objects don't politely walk out the door, they are flung. A passing giant planet, maybe a Jupiter-like behemoth, could have hurled it outward through gravitational interactions. In our solar system, Jupiter plays that role often, acting as both shield and slingshot. Computer simulations show that young gas giants are extremely efficient at ejecting debris into interstellar space. Historians still argue whether our own Jupiter ultimately protected Earth from excessive impacts or instead destabilized enough material to make early bombardment worse. The debate is ongoing, lively, and occasionally fueled by strong conference coffee. Wherever 3I/Atlas formed, it likely experienced similar chaos. Picture it drifting too close to a massive planet, its orbit stretching into a long ellipse, then elongating further until, snap, it exceeded escape velocity. One final gravitational shove, and it was no longer bound to its home star. No ceremony. No goodbye parade. Just a steady acceleration into the dark between suns. Interstellar space is not dramatic in the way movies suggest. There are no swirling neon clouds on every corner. It is mostly vacuum, with perhaps 1 atom per cubic centimeter. If you tried to take a deep breath out there, you'd be waiting a very long time. 3I/Atlas wandered through that near-nothingness for millions or even billions of years. Cosmic rays bombarded its surface, altering its chemistry. Ultraviolet radiation slowly modified ices into more complex organic molecules, a process we've observed in laboratory simulations. Spectral studies of similar objects show that prolonged radiation exposure can darken surfaces, creating a crust rich in carbon compounds called tholins. These substances give many outer solar system bodies their reddish hue. So when you look at 3I/Atlas glowing faintly above Mars, you might be seeing the cumulative result of eons of particle impacts and chemical rearrangements. It's less a pristine snowball and more a well-traveled fossil. There's also a quirky hypothesis some researchers whisper about, that interstellar objects might occasionally originate not from protoplanetary disks but from disrupted exoplanets themselves. Imagine a collision so catastrophic it ejects crustal fragments into deep space. If that happened, 3I/Atlas could, in theory, contain minerals formed inside a fully differentiated world. That idea remains speculative, but it adds a delicious layer of mystery. You're not just watching debris, you might be watching a shard of someone else's lost planet. As it approaches the Sun, the object begins to warm. Even at Mars' distance, about 1.5 astronomical units from the Sun, solar radiation is strong enough to sublimate volatile ices. Carbon monoxide and carbon dioxide can vaporize at relatively low temperatures. If 3I/Atlas contains these compounds, faint jets may already be venting from its surface. Those jets create a coma, a thin halo of gas and dust surrounding the nucleus. When 2I/Borisov passed through our solar system in 2019, astronomers confirmed it behaved very much like a typical comet, complete with a visible tail. That was reassuring in a way. The universe, at least in that instance, played by familiar rules. Whether 3I/Atlas will conform so neatly is still unfolding. Early observations suggest cometary activity, but its velocity and trajectory are distinctly hyperbolic, far exceeding the escape speed of the Sun. That's the telltale sign of an interstellar origin. You picture its speed numerically. Tens of kilometers per second relative to the Sun, fast enough to cross the distance between Earth and the Moon in a matter of hours. From Mars, it feels like a swift but stately arc. In reality, it is barreling through the inner solar system with breathtaking momentum. Mars, meanwhile, rotates calmly beneath you. A day here, called a sol, lasts about 24 hours and 39 minutes. That extra 39 minutes feels like Mars hitting the snooze button. Rovers like Perseverance and Curiosity operate on this slightly longer schedule, their teams on Earth adjusting sleep cycles during missions. It's a charming reminder that even robotic exploration comes with jet lag. As 3I/Atlas draws nearer, orbiters circling Mars, like the Mars Reconnaissance Orbiter, would be pivoting instruments to capture data. High-resolution cameras, spectrometers, and particle detectors can all contribute to understanding the visitor's composition. Even if the object passes millions of kilometers away, sensitive instruments can analyze reflected sunlight to decode its chemical fingerprint. Historians still argue whether interstellar objects are common and we're only now detecting them due to improved technology, or whether they are genuinely rare events. Before 2017, we had never confirmed one. Now, within a decade, we've identified 3. That suggests detection methods, wide-field surveys like ATLAS, are finally sensitive enough to catch these fleeting travelers. It may be that thousands pass through the solar system unnoticed each century. We simply lacked the cosmic security cameras. You continue watching the sky. The object's origin story feels both alien and intimately connected. After all, our Sun itself formed in a stellar nursery, likely alongside hundreds or thousands of sibling stars. Over billions of years, those siblings drifted apart across the Milky Way. It's entirely possible that 3I/Atlas originated in a system born from the same cluster as ours, astronomical cousins meeting unexpectedly after eons apart. The thought is strangely comforting. Mars remains silent beneath your boots. The wind is almost non-existent in this thin air. Above, the interstellar wanderer glows faintly brighter as it descends deeper into solar warmth. It carries with it the memory of another star's gravity, another planetary system's architecture. And right now, it is doing one very specific thing. It is approaching Mars, not with intention, not with awareness, but with the inevitability of physics. You keep your gaze fixed upward as the distance closes, kilometer by kilometer, second by second, the ancient traveler revealing, slowly, patiently, the story of where it began. You don't actually see 3I/Atlas with your own Martian eyes at first. Not really. Its story begins on Earth, under dark skies in Hawaii, Chile, and South Africa, where the Atlas telescopes sweep the heavens every clear night like vigilant lighthouse beams. The asteroid terrestrial impact last alert system was built with a practical, slightly anxious mission: find anything that might hit Earth before it does. It's planetary defense with a caffeine habit. Each Atlas unit uses wide-field cameras that scan enormous swaths of sky, comparing fresh images against previous ones. Software hunts for tiny shifts, pinpricks of light that move relative to the background stars. Most of these are ordinary near-Earth asteroids. Occasionally, a comet flares into view. But then, one night, a faint dot moves too fast, too straight, too committed. The detection pipeline flags it. Astronomers check the data. The object's motion doesn't fit a closed, elliptical orbit around the Sun. Instead, the preliminary calculations show an eccentricity greater than 1. In orbital mechanics, that's the magic number. Less than 1. You're bound to the Sun exactly 1? A parabolic escape. Greater than 1. You're just visiting. That was precisely how Oumuamua revealed itself in 2017, a mainstream historical moment that electrified astronomy. Its hyperbolic trajectory made it the first confirmed interstellar object. When 2I/Borisov followed in 2019, again with a hyperbolic orbit, scientists felt a mix of astonishment and validation. The galaxy was sending us samples. Now Atlas has done it again. You imagine the astronomer on duty, perhaps sipping lukewarm coffee, staring at orbital fit residuals that refuse to settle into a neat ellipse. There's a quiet thrill in those numbers. Not fireworks, more like a rising hum in the chest. Because if the math holds, this isn't just another rock. It's a messenger from beyond the Sun's gravitational family. Follow-up observations begin almost immediately. Other observatories pivot their telescopes toward the coordinates. Within hours, more data points refine the orbit. The hyperbolic excess velocity, the speed relative to the Sun when far away, confirms it. 3I/Atlas is inbound from interstellar space. Historians still argue whether Oumuamua's strange acceleration was due entirely to outgassing or whether more exotic explanations deserve consideration. That debate lingers in the background of every new interstellar detection. Because once you've seen something odd, you start looking for oddities everywhere. It's like hearing a bump in the night once and then never trusting your house again. Early brightness measurements of 3I/Atlas suggest it's larger than Oumuamua, possibly comparable to or bigger than 2I/Borisov's nucleus, which was estimated at roughly 1 kilometer across. Size estimates are tricky. Astronomers rely on reflected sunlight, which depends on both actual size and surface reflectivity, known as albedo. A small, highly reflective object can masquerade as a larger, darker one. It's cosmic catfishing, essentially. Spectroscopy begins next. By spreading the object's light into its component wavelengths, scientists search for absorption features, chemical fingerprints. Water ice produces distinct signatures. So do carbon monoxide, methane, and more complex organics. Even subtle slopes in the spectrum can hint at surface composition. From Mars, you imagine the data flowing like a quiet river of photons across millions of kilometers, captured by silicon detectors on Earth. Each pixel holds a fragment of the object's identity. There's also the matter of rotation. Variations in brightness over time can reveal how fast 3I/Atlas is spinning. Oumuamua famously displayed unusual brightness fluctuations, leading to models suggesting it was elongated, perhaps cigar-shaped or pancake-like. That sparked endless headlines and at least one very enthusiastic alien probe hypothesis. In reality, elongated asteroids are not unheard of, but the shape was extreme enough to raise eyebrows. With 3I/Atlas, astronomers watch for periodic dimming and brightening. If the light curve repeats every few hours, that's likely its rotation period. A rapid spin could indicate past collisions. A slow tumble might suggest structural fragility. Comets, in particular, can spin up as jets of gas act like thrusters, altering angular momentum. Physics is nothing if not opportunistic. Meanwhile, orbital projections show something intriguing. Its inbound path will carry it relatively near Mars' orbit before perihelion, the closest point to the Sun. Not a direct hit. Not even especially close by human standards. But, in astronomical terms, close enough to matter observationally. Mars becomes an unintended witness. The red planet has no global magnetic field today, only patchy crustal remnants. Its atmosphere is thin, about 1% of Earth's surface pressure. If 3I/Atlas sheds dust, some of that material could intersect Mars' orbital path. Tiny grains, perhaps no larger than sand, drifting in solar radiation. If even a fraction enters Mars' atmosphere, they would burn up as meteors, brief streaks of light across the dusty sky. You picture Perseverance's cameras catching a faint meteor trail, an interstellar shooting star over Jezero crater. That would be poetic, a rover searching for ancient Martian life while bits of another star system flash overhead. There's a quirky historical parallel here. In 1910, when Halley's Comet passed Earth, public panic erupted over fears that its tail, known to contain cyanogen gas, might poison the atmosphere. Entrepreneurs sold comet pills and bottled air. In reality, Earth passed harmlessly through the tail with no measurable effect. The episode remains a charming reminder that humans sometimes overreact to celestial events. With 3I/Atlas, the risk is essentially non-existent. Its path is well calculated. Mars is not in danger. Earth is not in danger. The real drama lies in measurement, not survival. As new data refine its orbit, uncertainties shrink. The hyperbolic arc becomes precise. You can almost draw it with a steady hand, inbound from above the ecliptic plane, curving around the Sun, passing near Mars' orbital distance, then accelerating outward forever. Forever is not hyperbole here. Once it escapes the Sun's gravity, it will drift into the galaxy again, perhaps encountering another star system millions of years from now. Maybe another set of astronomers, alien or otherwise, will notice it. Or maybe it will wander unseen for eternity. From your Martian vantage point, the light brightens fractionally each sol. The discovery phase is complete. The object has a name, a trajectory, a growing stack of observational data. And it is still coming. Not with malice. Not with intent. Just with the quiet inevitability of motion set in place long before Mars had a sky to cross. You begin to sense the geometry of it all, the invisible scaffolding that guides 3I/Atlas toward Mars' neighborhood. Space may look chaotic, but it runs on quiet mathematics. Every object moves according to gravity's patient instructions, tracing curves through spacetime like dancers following choreography written billions of years ago. Right now, 3I/Atlas is descending toward the Sun from above the ecliptic plane, the flat, disk-like region where most planets orbit. Mars circles the Sun at an average distance of about 1.52 astronomical units, taking roughly 687 Earth days to complete a year. That's a mainstream orbital fact, the kind printed in textbooks and etched into mission planning software. The interstellar object's path is hyperbolic, meaning its total energy relative to the Sun is positive. In simpler terms, it's going too fast to be captured. As it falls inward, solar gravity accelerates it further, bending its trajectory into a graceful curve. Think of skipping a stone across water. The sun is the pond, and 3I/Atlas is the stone, except instead of splashing, it bends and slingshots onward. Mars just happens to be near that bend. Orbital mechanics is less about coincidence and more about timing. Planets move. Comets move. Interstellar objects move very quickly. For 3I/Atlas to pass near Mars' orbital distance, Mars itself must not be somewhere else in its 687-day journey. Fortunately, or intriguingly, the geometry lines up so that when the object crosses roughly $1.50 from the Sun, Mars is not terribly far away in its own orbit. Not a bullseye, but close enough for astronomers to perk up. Historians still argue whether the early migration of giant planets, particularly in models like the NICE model, dramatically reshaped the architecture of the solar system or whether those migrations were more modest. That debate matters here because orbital resonances and gravitational nudges determine how objects travel across planetary systems. In our solar system's youth, shifting giants may have scattered countless icy bodies inward and outward. 3I/Atlas likely experienced something similar in its home system before being ejected entirely. As it approaches perihelion, solar radiation intensifies. If volatile ices are present, sublimation increases. Jets erupt from sunlit regions, pushing dust and gas outward. These jets can subtly alter the trajectory, a phenomenon known as non-gravitational acceleration. It's small, but measurable. Comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft, displayed such effects clearly as it orbited the Sun. So astronomers must account for both gravity and outgassing when predicting how close 3I/Atlas will come to Mars. It's not just a simple curve, it's a curve with tiny thrusters firing unpredictably. From your imagined spot on the Martian surface, the object grows brighter each sol. Not dramatically, this isn't a Hollywood sky-filling spectacle, but enough to notice if you're looking. Against the thin, dusty atmosphere, it resembles a sharp, wandering star with perhaps the faintest hint of a tail if activity increases. Mars' atmosphere, composed mostly of carbon dioxide, is too thin to produce dramatic scattering effects like Earth's blue skies. Sunsets here are bluish at the center and reddish farther out, a reversed palette caused by dust particles. If 3I/Atlas sheds fine particles that intersect Mars' path, those grains could contribute to high-altitude meteors. They would streak quickly, ionizing the upper atmosphere in brief flashes. There's a quirky possibility scientists consider during such encounters: meteor showers on another planet caused by interstellar debris. On Earth, annual showers like the Perseids occur when our planet passes through streams left behind by comets. If Mars intersects even a tenuous dust trail from 3I/Atlas, orbiters might detect enhanced meteoroid activity. Imagine naming a meteor shower after a star system we've never seen. Very on-brand for astronomy, naming things after mysteries. Meanwhile, calculations refine the closest approach distance. Let's say, hypothetically, it passes several million kilometers from Mars. That sounds enormous, and it is, but in astronomical terms, it's a near-miss worth studying intensely. For comparison, Mars' moon Phobos orbits at just 6,000 kilometers above the surface. So 3I/Atlas will not be buzzing Olympus Mons like an overeager drone. It's more of a distant flyby. Still, gravity connects them briefly. Mars will tug ever so slightly on the object as it passes. The deflection will be minuscule compared to the Sun's influence, but measurable. And in return, 3I/Atlas exerts an equally tiny pull on Mars, so small it would barely register even with our most sensitive instruments. If planets had feelings, Mars probably wouldn't even notice. You picture mission control teams adjusting spacecraft orientation. The Mars Reconnaissance Orbiter, MAVEN, perhaps even the aging Odyssey spacecraft, all turning their instruments toward the predicted coordinates. MAVEN, which studies the Martian atmosphere, could look for changes in ionization levels if dust influx increases. That would be subtle science, measuring slight upticks in charged particles as interstellar grains vaporize. There's also the matter of light travel time. Signals from Mars to Earth take anywhere from about 4 to 24 minutes depending on planetary alignment. So any observation of 3I/Atlas near Mars arrives with a built-in delay. By the time you see the data, the object has already moved on. Astronomy is always a little bit nostalgic that way. Some fringe voices inevitably whisper, what if its trajectory is not purely natural? After Oumuamua's odd acceleration, a few researchers proposed the possibility of a light sail, an artificial origin. Most of the scientific community favors natural explanations, like asymmetric outgassing. With 3I/Atlas, the default assumption remains natural. But the mere existence of prior anomalies ensures that data will be scrutinized carefully. Once you've been surprised, you double-check everything. From your Martian plane, the object reaches peak brightness near its closest solar approach. It arcs gracefully, a silver hook against fading twilight. Then, as it begins climbing outward, its speed increases again. That's the paradox of hyperbolic motion. The closer it gets to the sun, the faster it goes, and once it swings around, it departs even more swiftly than it arrived. Mars' role in this drama is observational, not catastrophic. The red planet is not being attacked, altered dramatically, or transformed overnight. It is simply being passed. Brushed by a traveler that formed under alien starlight. And yet, as you watch that arc trace across the sky, you realize something quietly profound. Mars has just been approached by matter older than its own crust, forged in a stellar environment utterly different from the one that shaped this dusty world. For a brief moment in cosmic time, two star systems overlap, not physically merging, not colliding, but intersecting in the most delicate way possible. A flyby governed by gravity and chance alignment. The curve completes. The bend around the sun is nearly finished. And 3I/Atlas, having skimmed past Mars' orbital realm, begins its long climb back toward the interstellar dark. As 3I/Atlas swings through the inner solar system, you start asking the most human question imaginable. How big is it? It's funny, isn't it? Faced with an object older than civilization, older than Mars' largest volcano, possibly older than complex life on Earth, and your brain still wants a number. Diameter, please. Preferably in kilometers. From Earth, and from orbit around Mars, astronomers don't get to stretch out a measuring tape. They rely on brightness. The object reflects sunlight, and that reflected light reaches telescopes as a faint signal. By calculating its absolute magnitude, how bright it would appear at a standardized distance, they can estimate size. But here's the catch. Brightness depends on reflectivity, or albedo. A charcoal briquette and a snowball of the same size would look very different in sunlight. Most cometary nuclei in our solar system have low albedos, often around 0.04, meaning they reflect only about 4% of the sunlight that hits them. They're darker than asphalt. That's a mainstream fact confirmed by spacecraft visits to comets like Halley and 67P. If 3I/Atlas behaves similarly, then its measured brightness suggests a nucleus perhaps 1 to several kilometers across. Not planet-killer territory, but not a pebble either. If, however, its surface is unusually reflective, perhaps coated in fresher ice exposed by recent outgassing, then it could be smaller than initial estimates suggest. That uncertainty keeps astronomers cautious. Early numbers are always provisional. Space has a way of humbling confident guesses. You imagine the nucleus tumbling slowly as it approaches Mars' orbital distance. Brightness measurements over time produce a light curve, a graph of intensity versus time. If the curve oscillates regularly, that's rotation. A repeating pattern every 8 hours? That's your spin period. 12 hours? Slower rotation. Irregular fluctuations? Perhaps it's not spinning neatly at all, but tumbling chaotically. Oumuamua famously displayed dramatic brightness variations, up to a factor of 10, implying an elongated shape, possibly cigar-like or pancake-like depending on the model. Historians still argue whether its shape was truly extreme or whether complex light scattering effects exaggerated the data. With 3I/Atlas, astronomers are watching carefully for similar oddities. So far, the light curve appears more modest. Let's say it varies by a factor of 2 or 3. That would suggest an irregular but not outrageous shape, lumpy, perhaps, like a cosmic potato. Which, to be fair, is the standard aesthetic for small bodies in space. No one expects a perfect sphere unless gravity is strong enough to force it there. And at a kilometer or two across, gravity barely wins arguments. Then there's composition. Spectroscopy is where the real detective work happens. When sunlight reflects off 3I/Atlas and enters a spectrograph, it spreads into a rainbow of wavelengths. Dark absorption lines reveal which molecules are present. Water ice has distinctive features in the infrared. Carbon monoxide and carbon dioxide each leave their own subtle fingerprints. Early spectra hint at volatile activity, faint emissions consistent with sublimating ices. That's comforting, in a way. It suggests 3I/Atlas is behaving like a comet, not some inert metallic shard. Carbon monoxide, in particular, can sublimate at relatively low temperatures. Even far from the Sunday 2I/Borisov showed strong carbon monoxide emissions, stronger than many solar system comets at comparable distances. If 3I/Atlas shares that trait, it may indicate formation in a very cold region of its home system. Cold formation zones tend to preserve primordial chemistry. That means 3I/Atlas could contain complex organic molecules formed in interstellar clouds before its parent star even ignited. Laboratory experiments have shown that ultraviolet radiation interacting with simple ices can create amino acid precursors. Not life, but ingredients. The galaxy may be running a slow, quiet chemistry experiment everywhere at once. There's also color. Many small bodies are categorized by spectral slope, how red or neutral their reflected light appears. Outer solar system objects, like Kuiper belt bodies, often exhibit reddish hues due to radiation-processed organics called tholins. If 3I/Atlas appears similarly red, that would align it with icy populations. If it's more neutral or even bluish, that might suggest different surface evolution. A quirky fringe idea occasionally pops up in discussions. What if interstellar objects have exotic compositions we've never encountered? Unusual ratios of isotopes, perhaps, or minerals rare in our solar system. Scientists would love to measure isotopic abundances directly, but from this distance, that's extraordinarily difficult. Still, subtle spectral anomalies could hint at differences. So far, nothing screams alien metallurgy. No suspicious glints of manufactured alloys. Sorry to disappoint the sci-fi fans. As 3I/Atlas nears its closest approach to Mars' orbital region, thermal models become important. How quickly does its surface heat? How deep does that heat penetrate? Comet nuclei are often porous, like dirty snowbanks. Heat can trigger outgassing beneath the surface, causing jets to erupt unpredictably. Those jets not only release gas and dust but can also torque the nucleus, altering its spin rate. You picture a jet flaring from one hemisphere, sunlight striking an icy patch, vapor blasting outward in a shimmering plume. The recoil nudges the object ever so slightly, like a minuscule rocket engine. Over days or weeks, that thrust can measurably change rotation. Comet 103P/Hartley 2, visited by NASA's epoxy mission, displayed such active jets in 2010, a confirmed example of rotational evolution driven by outgassing. If 3I/Atlas begins spinning faster as it approaches the Sun, astronomers will notice the light curve tightening. Too much spin, and structural integrity becomes an issue. Small bodies are often rubble piles, loose aggregates held together by weak gravity. Spin them too quickly, and they can shed material. That debris could form a temporary dust cloud trailing behind, subtle, but detectable. Meanwhile, Mars watches silently. Orbiters collect data, measuring reflected spectra from a slightly different vantage point than Earth-based telescopes. That dual perspective can refine models. It's a bit like examining a gemstone from two angles to understand its facets. You stand beneath the thin Martian sky, imagining the nucleus now defined in scientific papers not just as a streak of light, but as a rotating, outgassing, kilometer-scale relic of another planetary system. Its size constrained within error bars. Its spin estimated within hours. Its chemistry mapped in faint spectral lines. Not bad for something that spent eons wandering between stars. And yet, even with all these measurements, uncertainty lingers. Surface heterogeneity, subsurface composition, internal structure. Historians still argue whether cometary nuclei are mostly primordial aggregates or heavily altered by thermal evolution over billions of years. The same question now applies to this visitor. Is 3I/Atlas a pristine time capsule, or a weathered survivor? From your vantage point, it glows steadily, a small but undeniable presence. You now know roughly how big it is, roughly how fast it spins, roughly what it's made of. But roughly is the operative word. Because in astronomy, especially with interstellar wanderers, precision is hard-earned, and mystery is always part of the package. Mars does not panic. It does not glance nervously at the sky or send frantic messages to neighboring planets. It simply rotates, red and steady, as 3I/Atlas approaches its closest alignment with the planet's orbital path. But the machines orbiting Mars? They absolutely perk up. High above you, the Mars Reconnaissance Orbiter, MRO, slices through the thin upper atmosphere in a near-polar orbit, completing a lap roughly every 2 hours. Since arriving in 2006, a mainstream milestone in Martian exploration, it has mapped valleys, imaged dust storms, and spotted fresh impact craters. Now, its high-rise camera, capable of resolving features less than a meter across on the surface, is pointed outward instead of down. Not to photograph Martian rocks, but to capture a faint, fast-moving interstellar glow. You imagine the command sequence uploaded from Earth days earlier. Because of the light time delay, anywhere from several minutes to over 20, depending on planetary positions, these spacecraft operate with careful planning. There's no joystick control. No dramatic last-second steering. Engineers calculate precisely where 3I/Atlas will appear against the star field and program the instruments accordingly. MAVEN, the Mars Atmosphere and Volatile Evolution mission, also joins the effort. Since 2014, MAVEN has studied how solar wind strips away the Martian atmosphere, a process that likely transformed Mars from a wetter, thicker-aired world into the dry planet you stand on now. If dust from 3I/Atlas intersects Mars' upper atmosphere, MAVEN's particle detectors might register subtle increases in ionization. Tiny spikes. Brief signatures of interstellar grains vaporizing overhead. Historians still argue whether Mars lost most of its atmosphere primarily due to solar wind stripping after its magnetic field faded, or whether other processes, like large impacts, played an equally significant role. The data from MAVEN strongly supports solar wind erosion as a major factor, but debates remain about timing and magnitude. Now, this fleeting visitor offers a chance to study how fresh material interacts with the Martian environment in real time. Down on the surface, rovers like Perseverance continue their methodical work. They were not designed as skywatchers, but their cameras occasionally capture meteors. If even a whisper of debris from 3I/Atlas enters the atmosphere, a streak of light could flash above Jezero crater. Imagine the poetic timing. A rover searching ancient river deltas for signs of past microbial life while dust from another star burns briefly in the sky. Subtle, yes, but profoundly symbolic. You picture mission scientists refreshing telemetry feeds. Data trickles in, photon counts, spectral curves, plasma readings. No alarms. No dramatic spikes. Just careful measurements. The closest approach distance is now refined. Let's say several million kilometers separate Mars and 3I/Atlas at their nearest. To human intuition that sounds vast, and it is. But compared to the average Earth-Mars distance, which can exceed 200 million kilometers, it's relatively intimate. Not handshake close. More like a polite wave across a large canyon. There's no risk of impact. Orbital simulations, run thousands of times with slightly varied initial conditions, show no collision trajectory. Planetary defense experts breathe easily. This encounter is observational, not existential. Still, Mars' gravity exerts a faint tug as the object passes. Gravitational deflection calculations show that even a planet as modest as Mars can alter the path of a small body ever so slightly. The change in velocity, delta v, might be measured in meters per second. Insignificant compared to its tens of kilometers per second speed, but measurable with precise astrometry. It's like a gentle nudge as someone hurries past you in a hallway. There's also the sun's influence growing stronger near perihelion. Solar radiation pressure, the force exerted by photons themselves, can subtly push on dust particles released from the nucleus. For extremely small grains, light acts almost like wind. That's not science fiction, it's a well-measured physical effect. Spacecraft engineers even design solar sails to harness it intentionally. A fringe whisper inevitably surfaces again. What if 3I/Atlas displays non-gravitational acceleration too strong to be explained by outgassing? The memory of Oumuamua lingers in scientific culture. In that case, the observed acceleration was small but puzzling. Most researchers attribute it to comet-like jets that were simply too faint to detect directly. Still, the episode reminds everyone to keep an open, but disciplined, mind. So far, 3I/Atlas behaves. Its motion aligns with models that include modest outgassing. Nothing suggests artificial propulsion. No sudden course corrections. No blinking lights spelling out greetings. If it did, you'd expect at least one rover to attempt a selfie. As the object reaches its nearest alignment with Mars' orbit, brightness peaks. From your position on the Martian surface, it appears as a steady, sharp point, perhaps with a faint haze around it if activity is strong enough. The thin atmosphere offers little distortion. The stars look crisp here. Then, slowly, almost imperceptibly at first, it begins to recede. Hyperbolic motion ensures that once it rounds the Sun, it accelerates outward, climbing away from the inner solar system. Mars' orbit falls behind it. The geometry shifts. The polite wave across the canyon becomes a retreating silhouette. You think about how rare this alignment is. Interstellar objects may pass through the solar system more often than we once believed, but close approaches to planets are statistically uncommon. Most slip through the vast emptiness without brushing any world's orbital neighborhood so neatly. For a brief window, days, perhaps weeks, Mars has shared its celestial stage with a traveler from another star. No transformation. No scars. Just data. Measurements. Spectra. And yet, something subtle has happened. Instruments have captured photons reflected off material formed around a distant sun. Those photons have been converted into digital signals, transmitted across millions of kilometers, decoded by scientists on Earth. Knowledge has increased, incrementally, quietly. Mars remains unchanged in any visible way. The dust still shifts in faint breezes. The rovers continue drilling and sampling. Orbiters hum along predictable paths. But above, the interstellar wanderer has completed its closest dance with the red planet. And now, with increasing speed, it begins to leave. As 3I/Atlas pulls away from Mars' orbital neighborhood, one question lingers in every observatory and mission control room. What exactly are you? A comet? An asteroid? Something that refuses to fit neatly into either box? You've already seen hints of activity, faint jets, a whisper of coma. That leans comet. Traditionally, comets are icy bodies that originate in the outer reaches of planetary systems. When they approach a star, heat causes their volatile ices to sublimate, creating glowing comae and tails. Asteroids, by contrast, are generally rockier and less volatile, showing little to no outgassing. 2I/Borisov behaved unmistakably like a comet, complete with a well-defined tail. Oumuamua, however, complicated the picture. It showed no obvious coma, yet exhibited slight non-gravitational acceleration. Historians still argue whether that acceleration was caused by subtle outgassing of hydrogen or nitrogen ice, or whether entirely different mechanisms were at play. The debate remains lively, occasionally bordering on theatrical. With 3I/Atlas, the evidence so far suggests cometary behavior, but not extravagantly so. Its coma appears faint. Its tail, if present, is delicate, more suggestion than spectacle. From Mars' surface, you might not even notice a tail without magnification. It's less dramatic celestial brume, and more subtle cosmic smudge. Spectral analysis shows volatile compounds consistent with sublimating ices. Carbon monoxide emissions seem slightly stronger relative to water than in many solar system comets observed at similar distances. That could imply formation in a particularly cold region of its home system, far from its parent star. In our own solar system, objects forming beyond Neptune often preserve such volatile rich compositions. There's a mainstream classification nuance here. The distinction between comets and asteroids has blurred over time. Some asteroids have shown comet-like activity. These active asteroids challenge old definitions. The line between rocky and icy bodies is less a sharp border and more a gradient. 3I/Atlas might sit somewhere along that gradient. You imagine holding a chunk of it in your gloved hand, if that were remotely survivable. Would it crumble like compacted snow mixed with dust? Or feel more like porous stone with icy veins threading through it? Spacecraft visits to comets, such as ESA's Rosetta mission to 67P, revealed surfaces darker and more rugged than many expected: cliffs, pits, and fractured plains. Comets are not fluffy snowballs. They are complex, geologically textured worlds in miniature. A quirky hypothesis floats through conference hallways. What if interstellar objects are systematically different from solar system comets? Perhaps planetary systems vary more dramatically than we assumed. Maybe 3I/Atlas contains unusual ratios of deuterium to hydrogen in its water, an isotopic fingerprint that could reveal the conditions of its birth environment. Measuring such ratios remotely is extraordinarily difficult, but not impossible with powerful telescopes. If its isotopic composition differs significantly from typical solar system comets, that would be profound. It would confirm that water chemistry varies widely between stellar nurseries. And that would ripple into bigger questions about planetary habitability across the galaxy. From Mars, the object's brightness begins to taper slightly as it recedes from peak solar heating. Outgassing slows. The coma thins. The nucleus, if you could resolve it, would appear more distinct again. Yet some anomalies remain subtle. Its rotation period seems stable, not dramatically altered by jets. Its spectral slope is moderately red, but not extreme. Nothing screams exotic beyond comprehension. Instead, it whispers something arguably more astonishing: familiarity. The galaxy, at least in this instance, seems to build small icy bodies in ways not entirely alien to us. You reflect on that. For decades, exoplanet discoveries have revealed diversity: hot Jupiters skimming stellar surfaces, super-Earths in tight orbits, planets with densities suggesting compositions we barely imagined. Planetary systems can be wildly different in architecture. Yet here is a fragment from another system behaving in ways your physics textbooks predicted. That consistency is comforting. Gravity works the same everywhere. Thermodynamics does not take creative liberties. Even in another star's nursery, ice sublimates under heat. Dust follows radiation pressure. Still, historians still argue whether the sample size, now 3 confirmed interstellar objects, is far too small to draw sweeping conclusions. Maybe we've simply been lucky, detecting the most comet-like examples because they brighten under solar heating. Perhaps countless inert, rocky interstellar asteroids pass through unnoticed because they remain too dim. Detection bias is a powerful force. You can't help but smile at the idea that the universe may be full of quiet, rocky interstellar drifters slipping by unseen, like cosmic introverts avoiding attention. 3I/Atlas just happens to be expressive enough to wave a faint, icy tail. Mars, for its part, remains an observer. No dramatic meteor storms erupt. No atmospheric upheaval follows. MAVEN's data shows no extraordinary spikes beyond minor, expected variations. The encounter is scientifically rich but physically gentle. As the object continues outward, its classification settles tentatively into interstellar comet. Papers will be written. Models refined. Error bars tightened. But the door remains open for revision. Science, after all, thrives on provisional labels. You stand beneath the fading arc of 3I/Atlas, now slightly dimmer against the Martian sky. The question of what it is has mostly resolved into familiar categories: ice, dust, rock, motion. And yet, beneath that familiarity lies something extraordinary. Because even if it behaves like a comet, even if its chemistry echoes what you already know, it was born under a different sun. Its atoms condensed in a disk you will never see. Its journey spans distances so vast that language strains to hold them. Comet or not, it remains a traveler from elsewhere. And it is still, steadily, leaving. As 3I/Atlas continues its outward climb, you start thinking less about the nucleus itself and more about the dust it leaves behind. Because comets, even subtle ones, are messy travelers. They shed. They trail. They quietly litter space with grains that range from microscopic specks to pebble-sized fragments. And Mars is drifting through that same region of space. Not directly through a thick, cinematic ribbon of debris. This isn't a glowing highway in the sky, but potentially through a sparse, diffuse stream of particles released during the object's closest solar approach. The geometry matters enormously. Dust does not simply follow the nucleus like obedient ducklings. Once ejected, each grain follows its own orbit, shaped by solar gravity and radiation pressure. Some lag behind. Some spread outward. Some spiral subtly due to the Poynting, Robertson effect, a well-established phenomenon where sunlight causes dust grains to slowly lose angular momentum and drift inward toward the sun. That's a mainstream astrophysical fact, measured and modeled for decades. Even light, gentle as it seems, can rearrange the solar system one dust mote at a time. If Mars intersects even a thin filament of 3I/Atlas debris, the result would be high-altitude meteors. Unlike Earth, Mars has an atmosphere only about 1% as dense at the surface. That means incoming particles penetrate deeper before burning up. The frictional heating would still cause most small grains to vaporize, producing streaks of ionized gas. But the visual effect would be fainter, briefer. No roaring fireballs. More like delicate scratches of light across a dim canvas. Orbiters are better suited than rovers to notice. Instruments aboard MAVEN can detect sudden increases in metallic ions, magnesium, iron, left behind when meteoroids ablate. Similar detections have been made before. In 2014, Mars passed through debris from Comet Siding Spring, and spacecraft recorded measurable atmospheric effects. That was a real, documented event. The comet passed within about 140,000 kilometers of Mars, extremely close in planetary terms, and delivered a temporary meteor storm. Historians still argue whether such cometary encounters over billions of years significantly altered Mars' atmospheric chemistry, or whether their cumulative contribution was minor compared to volcanic outgassing and solar wind loss. The Siding Spring event offered a rare modern analog, showing that while effects were noticeable, they were not transformative. With 3I/Atlas, the dust density appears far lower. So if Mars does encounter any grains, the effect will be subtle. Perhaps a slight uptick in ionization rates, a few extra streaks detected by sensitive cameras. Nothing that reshapes the planet. Nothing that startles a rover into existential reflection. You imagine standing under the Martian night as a tiny interstellar particle burns overhead. That grain may have condensed in a protoplanetary disk around a star you cannot name. It drifted for eons in frozen darkness. Then, for a fraction of a second, it becomes a streak of plasma in Mars' sky before dissolving into atoms again. There's something poetic about that life cycle. Stardust to streak to stardust again. A quirky idea sometimes floated in astrobiology circles is that interstellar dust grains could carry complex organic molecules between systems. Not intact organisms necessarily, that's far more speculative, but prebiotic compounds. Laboratory analyses of meteorites in our own solar system have revealed amino acids and other organic molecules formed in space. The famous Murchison meteorite, which fell in Australia in 1969, contained over 70 types of amino acids. That's a well-established scientific result. So if even a tiny fraction of 3I/Atlas dust reaches Mars' surface, surviving atmospheric entry in microscopic form, it could deposit exotic organics into the regolith. The amounts would be minuscule. You're not seeding forests here. But chemically speaking, it's an exchange between star systems. Of course, most particles will burn up completely, their atoms dispersing into the thin atmosphere. Mars' low gravity, about 38% of Earth's, means some of those atoms could even escape to space over time. The planet is not especially good at holding onto its lighter elements. Meanwhile, solar radiation continues to sculpt the departing debris trail. Smaller particles are pushed into slightly altered paths, creating a widening fan of dust. Larger fragments remain closer to the original trajectory. Over months and years, the stream disperses, becoming indistinguishable from the background population of interplanetary dust. You consider how Earth experiences meteor showers annually because it repeatedly crosses well-established debris streams from periodic comets. Mars, too, has predicted meteor showers, though they are less studied. Adding an interstellar component, even a faint one, introduces a new category entirely: meteor activity sourced from another star. It sounds dramatic. In reality, it would be subtle. Science often is. From orbit, instruments scan for anomalies. A slight enhancement in plasma density here. A faint optical flash there. Data accumulates quietly, line by line. No alarms blare. No headlines scream, "Mars under attack." Though you can imagine certain tabloids trying very hard. And yet, the significance lies not in spectacle but in confirmation. If even a few particles are conclusively linked to 3I/Atlas, that proves material exchange between star systems is not just theoretical. It is measurable, observable. Historians still argue whether panspermia, the transfer of life or its precursors between worlds, is plausible on galactic scales. The distances are immense. The radiation harsh. Survival times uncertain. But events like this demonstrate at least the physical mechanism exists. Matter moves between stars. Not often. Not abundantly. But undeniably. You watch the sky again. The nucleus is fainter now, the coma thinning as it recedes from solar warmth. Its dust trail disperses into near invisibility. Mars remains largely unchanged. No new craters appear from this encounter. No atmospheric transformation unfolds. The red planet continues its quiet rotation, dust devils wandering lazily across plains older than complex life on Earth. But somewhere in the upper atmosphere, perhaps a single interstellar grain flashes briefly into plasma before vanishing. And that fleeting spark is enough to remind you, Mars has just tasted something born around another sun. Now comes the question that always sneaks in, no matter how calm the data looks. Could it hit? You try to keep your voice steady, scientific, unbothered. But somewhere deep in your evolutionary wiring is a small primate ancestor who remembers that falling rocks are bad news. So yes, you ask it plainly, could 3I/Atlas collide with Mars? Short answer, no. Longer, more satisfying answer. The orbital solutions say the probability is effectively zero for this passage. Astronomers run thousands, sometimes millions, of simulations, slightly adjusting initial measurements within their uncertainties. These Monte Carlo simulations map out a cloud of possible trajectories. For 3I/Atlas, that cloud does not intersect Mars. Not even close enough to raise eyebrows in the planetary defense community. And planetary defense people are paid to raise eyebrows. A mainstream historical fact helps ground you here. Large impacts absolutely have shaped Mars in the past. The Borealis Basin, which covers much of the northern hemisphere, is widely believed to be the result of a colossal impact early in Martian history. We're talking about an object possibly thousands of kilometers wide smashing into young Mars over 4 billion years ago. That event likely reshaped the planet's crust dramatically. So yes, Mars has been hit before. Hard. But 3I/Atlas is not on that kind of trajectory. Even if, hypothetically, it were aimed directly at Mars, size matters. Current estimates place its nucleus at perhaps 1 to several kilometers across. An impact of that scale would create a significant crater, tens of kilometers wide, and inject dust into the atmosphere. On Mars, with its thin air and lack of global oceans, the environmental consequences would differ from Earth's, but it would still be dramatic locally. However, we are not in that scenario. The closest approach distance is measured in millions of kilometers. That's dozens of Mars diameters away. To put it in perspective, Mars' radius is about 3,390 kilometers. So even a close flyby at, say, 3 million kilometers is nearly 900 Mars radii away. That's not a near miss in impact terms. That's comfortably distant. Historians still argue whether the frequency of large impacts in the early solar system declined smoothly over time or whether there were episodic spikes caused by orbital instabilities among the giant planets. That debate matters when you look at crater records. But for modern times, the inner solar system is comparatively calm. Large impacts are rare on human timescales. Interstellar impacts would be rarer still. The density of interstellar objects passing through any given planetary orbit is extremely low. Even if thousands traverse the solar system each million years, the vastness of space makes direct collisions improbable. Planets are small targets in a very large shooting gallery. Still, your imagination wanders. What if Mars had been directly in its path? The relative velocity would be enormous, likely tens of kilometers per second. Higher than many typical asteroid impacts because of the hyperbolic excess speed. That means more kinetic energy for the same mass. The equation is simple and unforgiving. Kinetic energy equals 1/2 mass times velocity squared. Double the speed, quadruple the energy. Physics does not negotiate. A high-speed impact could excavate deep crustal material, perhaps even expose subsurface ice. Some researchers speculate that past impacts may have temporarily thickened Mars' atmosphere by vaporizing ice and releasing gases. Others argue the net long-term effect of repeated impacts may have contributed to atmospheric loss instead. The balance between delivery and erosion remains an active area of study. But again, 3I/Atlas is not striking Mars. It is passing. There's also the gravitational focusing effect to consider. Massive bodies slightly increase their effective cross-section for collisions because their gravity pulls incoming objects inward. For Earth, this effect enhances impact probability modestly. Mars, being smaller and less massive, has a weaker focusing effect. Even if 3I/Atlas path were somewhat closer, Mars' gravity would not dramatically bend it inward from millions of kilometers away. A quirky historical parallel surfaces in your mind. In 1994, Comet Shoemaker, Levy 9 impacted Jupiter after being torn apart by tidal forces. The resulting scars were visible from Earth-based telescopes. That event was a vivid reminder that planetary impacts are not ancient history, they still occur. Jupiter's enormous gravity makes it a cosmic vacuum cleaner, sweeping up debris that might otherwise wander inward. Mars does not enjoy that luxury. It's more of a modest apartment with minimal security. But tonight, security is unnecessary. The trajectory is clean. From your Martian vantage point, 3I/Atlas is already receding. Its brightness diminishes steadily. No ominous swelling in the sky. No growing roar. Just a quiet fading point of light. You feel almost disappointed by how non-apocalyptic this all is. Evolution wired you for drama, but the universe often delivers subtlety instead. Yet subtle does not mean insignificant. The fact that you can calculate an interstellar object's path with such precision, predicting millions of kilometers flybys years in advance, is itself astonishing. Newton's laws, refined by Einstein's relativity, continue to describe motion across unimaginable distances. Gravity's equations, written centuries ago, still hold. Historians still argue whether future improvements in detection technology will reveal many more interstellar objects, perhaps even some on trajectories closer to planets. Surveys like the Vera C. Rubin Observatory are expected to dramatically increase discovery rates. If so, planetary defense models will expand to include not just solar system natives, but true interstellar visitors. For now, though, Mars is safe. The red planet bears no new scar from this wanderer. Its ancient craters remain untouched by 3I/Atlas. The object continues outward, carrying with it the gravitational fingerprint of its brief encounter. Mars tugged on it, ever so slightly, altering its outbound path by a whisper. That deflection will persist for millions of years as it travels on. So in a way, Mars has marked it, not with a crater, but with a curve. And that curve is the only trace of their near meeting. As 3I/Atlas climbs away from the Sun and drifts beyond Mars' orbital distance, you begin to notice something subtler than dust, subtler than gravity. You notice the invisible weather of space itself. Because space is not empty. Not really. It is filled with the solar wind, a continuous stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. Mostly protons and electrons, this plasma bathes every planet, every comet, every drifting grain of dust in the solar system. Mars feels it directly. Unlike Earth, which is shielded by a strong global magnetic field generated by its molten outer core, Mars lost its global magnetosphere billions of years ago. That's a mainstream scientific conclusion supported by data from missions like Mars Global Surveyor and MAVEN. What remains are patchy crustal magnetic fields, localized remnants frozen into ancient rocks. But globally, Mars stands exposed. So when 3I/Atlas sweeps past Mars' orbital region, it isn't just interacting with sunlight. It's plowing through solar wind. You picture the comet's coma, a thin cloud of gas expanding outward from the nucleus. As neutral gas molecules drift away, solar ultraviolet radiation ionizes some of them, stripping electrons and creating charged particles. These ions are then caught by the solar wind's magnetic field and swept into a tail that points generally away from the Sun. That's why comet tails don't trail behind like hair in the wind. They point away from the Sun, regardless of the comet's direction of travel. It's a delightful cosmic illusion. If comets had social media accounts, they'd constantly be accused of flying backward. With 3I/Atlas, the interaction may be faint but measurable. Instruments on Mars orbiters can detect fluctuations in plasma density as the solar wind flows past both the planet and the comet's expanding ion cloud. If the geometry aligns just right, Mars could briefly find itself downstream of a faint extension of the comet's ion tail. Historians still argue whether solar wind stripping alone can account for the full loss of Mars' early thick atmosphere, or whether impacts and internal geologic decline contributed equally. But there's no debate that solar wind plays an active role today. MAVEN has directly measured atmospheric ions being carried away into space. Mars is slowly, steadily leaking. Now imagine a subtle twist: interstellar ions, born from 3I/Atlas outgassing, caught in the same solar wind stream that is eroding Mars. For a fleeting time, particles from another star system are entangled in the same plasma flow that shapes the red planet's fate. The physics is elegant. Charged particles spiral along magnetic field lines. Shocks form where solar wind meets obstacles. Comets create bow shocks, regions where the supersonic solar wind slows and diverts around the expanding coma. Even a relatively small comet can carve out a temporary magnetic bubble tens of thousands of kilometers wide. If 3I/Atlas is sufficiently active, it too will generate such a structure. Mars, meanwhile, creates its own induced magnetosphere as the solar wind interacts with its ionosphere. For a brief period, two plasma environments, one planetary, one cometary, exist in proximity. They don't collide dramatically, but they overlap in subtle ways. There's something quietly beautiful about that. Two bodies, both shaped by stellar winds, one born here, one born elsewhere, briefly sharing the same electromagnetic sea. You imagine the data plots: spikes, dips, oscillations in magnetic field strength. Plasma waves rippling outward. Nothing catastrophic. Just signatures. A quirky but real scientific detail: comet tails can stretch millions of kilometers. Some have been observed extending longer than the distance between Earth and the Sun. That doesn't mean they're dense or dangerous. Far from it. They are incredibly diffuse. But their reach is impressive. If 3I/Atlas develops a substantial ion tail, it could span a vast arc of space as it departs. Mars rotates beneath this invisible ballet. Dust storms may swirl on the surface, driven by seasonal heating. Up above, charged particles stream past at relentless speed. The Sun, meanwhile, is not constant. Solar activity rises and falls in roughly 11-year cycles. During solar maximum, flares and coronal mass ejections intensify the solar wind. If 3I/Atlas passage coincides with heightened solar activity, its tail could flicker and kink under variable magnetic pressure. Comet tails have been observed to disconnect suddenly when struck by solar eruptions, a phenomenon called a tail disconnection event. It's dramatic in images, though harmless at planetary distances. If such an event occurred now, astronomers would watch closely. A snapped ion tail from an interstellar comet near Mars would make for fascinating plasma physics. But even without drama, the steady shaping continues. Solar radiation pressure pushes on dust grains. Solar wind sculpts ion tails. Mars' weak gravity barely participates. The dominant force here is the Sun. And that's an important realization. 3I/Atlas may have been born under another star, but for this brief chapter, it is fully under the authority of ours. Its coma responds to our Sun's photons. Its ions dance to our Sun's magnetic field. Its trajectory bends in our Sun's gravity well. Stars, it seems, are territorial. Yet soon, very soon, it will escape again. Its hyperbolic excess velocity ensures it will climb out of the Sun's gravitational influence entirely. The solar wind's grip will fade. The photon pressure will weaken with distance. The ion tail will dissipate as activity ceases. And then it will re-enter the true interstellar medium, a different plasma environment, shaped by the collective winds of many stars and the magnetic field of the Milky Way itself. For now though, you stand on Mars beneath a sky touched by both solar wind and interstellar origin. The comet's faint tail streams away from the Sun like a banner of ionized memory. No explosions. No collisions. Just fields and particles, quietly weaving their influence. 3I/Atlas is not attacking Mars. It is not transforming it. It is simply passing through the Sun's domain, briefly brushing Mars' cosmic weather system, before continuing its endless drift between the stars. As 3I/Atlas fades farther from Mars, the immediate drama of flyby geometry and plasma tails gives way to something deeper, chemistry. Because long after the object becomes too faint to see with modest telescopes, its spectral data remains. And in those faint lines of light lies the real treasure, clues about another star system. You imagine astronomers poring over spectra the way historians pore over ancient manuscripts. Every dip in brightness at a specific wavelength corresponds to a molecule absorbing light. Water, carbon monoxide, methanol, perhaps traces of hydrogen cyanide. Each one is a chemical syllable in a story written billions of years ago. A mainstream scientific fact anchors this. We already know that protoplanetary disks around young stars contain many of the same molecules found in our own early solar system. Observations with radio telescopes like ALMA have detected carbon monoxide, formaldehyde, and even more complex organic compounds in distant stellar nurseries. Chemistry, it seems, is not parochial. So when 3I/Atlas reveals a familiar molecular inventory, it suggests something profound. Planetary building blocks may be broadly similar across the galaxy. Ice plus rock plus organics equals planetesimals. Different stars, same recipe, at least in broad strokes. But the details matter. Is the ratio of carbon monoxide to water higher than in typical solar system comets? Does the object show depletion in certain volatiles? These differences can hint at the temperature and radiation environment in which it formed. In our solar system, the concept of snow lines defines distances from the Sun where specific compounds condense into ice. Water freezes closer in, carbon monoxide requires colder regions farther out. If 3I/Atlas is especially rich in highly volatile ices, it may have formed beyond its system's equivalent of Neptune. Historians still argue whether the diversity of exoplanetary systems we observe, hot Jupiters, super-Earths, tightly packed inner planets, implies equally diverse small body populations, or whether small icy bodies form in broadly similar ways regardless of planetary architecture. Interstellar objects like this are rare physical samples that can inform that debate. There's also isotopic chemistry to consider. On Earth, the ratio of deuterium to hydrogen in water provides clues about the source of our oceans. Measurements of comets have shown a range of deuterium levels, some matching Earth's oceans, others significantly higher. If 3I/Atlas water, if measurable, shows a wildly different isotopic ratio, that would underscore the chemical individuality of its home system. You like that thought? Individuality within universality. Same physics, different fingerprints. A quirky but fascinating tidbit: some meteorites in our own collection contain pre-solar grains, tiny mineral inclusions that predate the Sun itself. These grains formed around other stars and survived incorporation into the solar nebula. We've literally held stardust older than our solar system in laboratory tweezers. That's not poetic exaggeration, it's measured through isotopic anomalies. In that sense, 3I/Atlas is like a supersized pre-solar grain, except instead of being trapped in a meteorite, it remained intact and wandered freely until now. As data accumulates, models of its origin become more refined. Its incoming velocity relative to the Sun, its hyperbolic excess speed, provides clues about its birthplace. By tracing that velocity vector backward, astronomers can estimate its direction of origin in the galaxy. Pinpointing a specific star is nearly impossible due to gravitational perturbations over millions of years, but broad regions can sometimes be suggested. Perhaps it originated from a relatively young stellar population. Or perhaps from the galactic thin disk, like our Sun. The Milky Way rotates, stars orbiting its center over hundreds of millions of years. 3I/Atlas has been riding those currents long before humans learned to chart the sky. You consider how small it is compared to the scales involved. A kilometer-wide object crossing distances measured in trillions of kilometers. And yet, it carries information. That's the astonishing part. Information survives. Radiation alters surfaces, yes. Cosmic rays darken and chemically modify ices. But bulk composition remains. The ratios of elements, the presence of certain molecules, these endure. Even after millions of years adrift, 3I/Atlas still bears the signature of its birth environment. Mars, meanwhile, has its own chemical story. Rovers have found evidence of ancient river deltas, clay minerals formed in water, and organic molecules preserved in sedimentary rocks. The Red Planet once hosted conditions potentially suitable for microbial life. That's not speculation, it's supported by rover data from missions like Curiosity and Perseverance. Now imagine comparing Mars' ancient chemistry with that of 3I/Atlas. One world shaped by our Sun, one fragment shaped by another. Similar building blocks. Different outcomes. Historians still argue whether life is likely common given the apparent ubiquity of organic chemistry, or whether the leap from chemistry to biology is so improbable that it may be rare. Interstellar objects add weight to the first half of that debate. Organic molecules are not unique to Earth. They are cosmic. As 3I/Atlas dims further, large telescopes continue tracking it for as long as possible. Each additional data point refines understanding. Eventually, it will become too faint, slipping beyond detection limits. But its spectral archive will remain, catalogued, analyzed, debated in journal articles and conference halls. You stand beneath the Martian sky, now darker, the object barely visible. It no longer dominates attention. Instead, its legacy shifts into data tables and chemical models. Mars has not been altered physically. No crater marks this passage. No atmospheric shift betrays its visit. But intellectually, the encounter changes something. Because now you know, not just theoretically, but observationally, that material from another star system can pass close to Mars and be studied in detail. You've tasted the chemistry of elsewhere. And in that chemistry, you glimpse the possibility that across the galaxy, planets may share more in common than you once imagined. 3I/Atlas continues outward, carrying with it a slightly altered trajectory thanks to Mars' gentle tug. And behind it, in servers and scientific papers, remains a growing understanding of how other suns build their worlds. Mars keeps rotating. The galaxy keeps turning. And somewhere in the data, another star's fingerprint quietly lingers. As 3I/Atlas shrinks into a dimmer point of light, your attention drifts downward, to the ground beneath your boots. Because Mars is already a museum of impacts. Long before this interstellar visitor skimmed past, the red planet endured eras when rocks fell from the sky with relentless enthusiasm. You kneel, carefully, because Martian regolith has the texture of powdered brick, and run your gloved hand across ancient terrain pocked with craters. Some are small and crisp, only a few meters across. Others stretch for hundreds of kilometers. One of the largest known impact structures, Hellas Planitia, spans about 2,300 kilometers in diameter. That's a mainstream geological fact, confirmed by orbital mapping. It's so vast it creates its own localized weather patterns. These scars mostly date back billions of years, particularly to a period known as the Late Heavy Bombardment, around 4 to 3.8 billion years ago. During that chaotic era, leftover debris from planetary formation rained down on the inner solar system. Earth was hit. The Moon was hit. Mars was hit. The difference is that Mars kept the receipts. Earth's plate tectonics and active erosion erased most early impact craters. Mars, lacking both active plate tectonics and abundant liquid water erosion in later epochs, preserved its ancient wounds like a geological scrapbook. You imagine 3I/Atlas arriving during that violent time instead of now. Back then, the inner solar system was crowded with wandering planetesimals. A hyperbolic interstellar object might not have seemed especially unusual. It would have joined a celestial demolition derby already in progress. Historians still argue whether the late heavy bombardment was a sharp spike triggered by giant planet migration, or simply the tail end of a gradually declining impact rate. The debate hinges on crater dating, lunar samples, and complex orbital models. But regardless of the exact timeline, early Mars endured a much harsher environment than the quiet sky you see tonight. And yet, here's the intriguing comparison. Most of the impactors that shaped Mars were born in the same solar nebula as the planet itself. They shared isotopic signatures, similar elemental ratios. 3I/Atlas, by contrast, carries foreign chemistry. If it had struck Mars, purely hypothetically, it would have added material not native to this system. A tiny admixture of another star's debris embedded in Martian crust. Over billions of years, countless microscopic interstellar grains may already have done exactly that. The difference is scale. There's a quirky, lesser-known idea that some unusual meteorites found on Earth might contain tiny traces of truly interstellar origin, grains whose isotopic signatures differ radically from solar system norms. While most meteorites originate from asteroids within our system, pre-solar grains inside them prove that foreign material can survive incorporation. It's not a stretch to imagine Mars harboring similar microscopic interstellar relics. You look toward the horizon where ancient highlands rise. The crater density there is immense, evidence of surfaces that have not been resurfaced in billions of years. In contrast, younger volcanic plains have fewer craters, their lava flows burying older scars. This technique, counting craters to estimate surface age, is a foundational method in planetary geology. More craters generally mean older terrain. Now consider the statistical rarity of an interstellar impact. Even during the early bombardment, most impactors likely originated within the same system. Interstellar objects, though present, would have been vastly outnumbered. So if Mars contains fragments from other stars, they are probably extraordinarily rare. Tiny chemical anomalies waiting to be identified. Mars' two small moons, Phobos and Deimos, add another wrinkle. Their origins remain debated. Some scientists argue they are captured asteroids. Others suggest they formed from debris thrown up by a large impact on Mars. Historians still argue which scenario fits best, based on orbital dynamics and composition. If capture is possible for small bodies, you briefly wonder, Could an interstellar fragment ever be gravitationally captured by Mars? In theory, yes, but only under very specific conditions, usually involving energy loss through atmospheric drag or multi-body gravitational interactions. For a fast-moving hyperbolic object like 3I/Atlas, capture is exceedingly unlikely. It simply has too much speed. Mars cannot hold onto it. You find that poetic. Mars bears countless scars from its own family's debris, yet when a true outsider passes by, it cannot keep it. The visitor comes and goes, leaving only data and a faint gravitational signature. Still, the comparison is illuminating. The craters beneath your feet remind you that planetary surfaces are shaped by impact. That violence once dominated this region. And against that backdrop, 3I/Atlas feels gentle. A whisper compared to ancient thunder. Even the Borealis Basin, if indeed caused by a giant impact, may have influenced Mars' long-term climate by altering crustal thickness and volcanic patterns. Some models suggest that early impacts could have temporarily warmed Mars, melting ice and creating transient rivers. Others argue that repeated impacts may have stripped atmosphere faster than it could accumulate. The interplay remains debated. But tonight, no basin forms. No shockwave ripples outward. The sky remains calm. 3I/Atlas is already far beyond its closest point. Its brightness fades into the background of stars. Soon, only powerful telescopes will track it. Then, eventually, none at all. Mars continues as it has for billions of years, scarred, silent, slowly cooling. You stand on ground shaped by countless collisions, watching an object that will not join that record. And you realize something subtle. Sometimes the most important encounters are the ones that don't leave craters. Because this time, Mars' ancient scars serve not as warnings, but as contrast. A reminder of what could have been, and what, in this case, beautifully was not. As 3I/Atlas recedes into the outer dark, its physical presence diminishes, but its possibilities expand. Because when you think about icy bodies crossing interstellar space, you inevitably arrive at the question that refuses to go away. What are they carrying? Not just rock. Not just frozen gases. But chemistry that might, under the right conditions, lean toward life. You remember that comets in our own solar system have been found to contain complex organic molecules. The Rosetta mission detected glycine, the simplest amino acid, in the coma of Comet 67P. That's a confirmed scientific result. Meteorites like Murchison, as you've already considered, contain dozens of amino acids formed in space. Organic chemistry is not rare. It is widespread, almost stubbornly so. So if 3I/Atlas formed in a cold outer disk around another star, bathed in ultraviolet radiation for eons, it may carry similar compounds. Carbon chains. Nitriles. Prebiotic ingredients assembled slowly in icy mantles long before any planet stabilized. Historians still argue whether comets delivered a significant fraction of Earth's water and organics during the early bombardment phase, or whether asteroids played the dominant role. Isotopic measurements muddy the picture. Some comets match Earth's ocean chemistry, others do not. The debate continues, layered and nuanced. Now extend that debate outward, across the galaxy. If icy bodies are routinely ejected from planetary systems, and if they routinely pass through others, then the exchange of organic material might be a natural, ongoing process. Not frequent on human timescales, but inevitable over cosmic time. You imagine a microscopic grain from 3I/Atlas surviving atmospheric entry on Mars. It settles gently into dust near Jezero crater. There it rests, inert perhaps, or slowly altered by radiation. The odds of its sparking life are vanishingly small. Mars today is cold, dry, and bathed in ultraviolet light. But billions of years ago, when Mars had flowing rivers and thicker air, conditions were more forgiving. Could interstellar visitors in that distant epoch have contributed organics to a young, wetter Mars? It's speculative, but physically plausible. There's a fringe extension of this idea known as lithopanspermia, the transfer of life between planets via rocks blasted into space by impacts. We know Martian meteorites exist on Earth. Dozens have been identified. That's not conjecture, it's laboratory confirmed by isotopic signatures matching Mars. So material exchange between planets is real. The leap to interstellar exchange is enormous in scale, but not forbidden by physics. Of course, survival across millions of years in interstellar radiation is harsh. Cosmic rays penetrate deep into exposed material, breaking molecular bonds. Some shielding, meters of rock or ice, would be necessary to protect complex molecules. Whether microorganisms could survive such a journey remains uncertain. Experiments on hardy organisms like tardigrades show remarkable resilience, but the timescales of interstellar travel stretch into millions of years. Historians still argue whether that makes panspermia probable or merely poetic. You feel the weight of that uncertainty. Science rarely hands out definitive answers in questions this grand. Instead, it offers probability curves and careful phrasing. Meanwhile, Mars rotates quietly. Its thin atmosphere glows faintly at sunset, blue near the sun, rust-red beyond. The sky darkens. 3I/Atlas is now barely distinguishable from background stars. Yet the data it left behind continues to whisper. Spectral lines indicating carbon-bearing molecules. Activity patterns suggesting preserved volatiles. Nothing extraordinary, no unmistakable biosignatures, but enough to confirm that the chemistry of life's ingredients is not unique to our sun's neighborhood. You consider how life on Earth emerged relatively quickly after the late heavy bombardment subsided. Within a few 100 million years, microbial life appears in the fossil record. Some scientists argue that if conditions are right, life may arise readily. Others caution that Earth could be an outlier, a statistical fluke in a vast cosmic lottery. Interstellar objects like 3I/Atlas add a quiet data point to that argument. They demonstrate that organic-rich material moves between stars. Not abundantly, not dramatically, but measurably. You feel your thoughts slowing now, stretching wider and softer, like the orbit of the object itself as it departs. The urgency of "what is it doing to Mars?" dissolves into a gentler realization. It is not attacking, not transforming, not seeding forests overnight. It is participating in a galaxy-wide circulation of matter. Ice becomes vapor, vapor becomes ion, ion drifts, dust settles, gravity nudges, stars exchange fragments over billions of years. Mars has simply been brushed by that circulation. No crater marks the encounter. No new mountain rises. But somewhere in the thin upper air, perhaps a single molecule once locked in alien ice joined the faint carbon dioxide breeze before escaping to space again. A fleeting exchange. You look up one last time. The wanderer is almost gone now, swallowed by distance. The red planet remains as it was, ancient, scarred, quietly beautiful. And the galaxy continues its slow, patient mixing of worlds. You let the image soften, a small icy body gliding outward into darkness, Mars turning below, the sun glowing steady at the center. Everything moving. Everything connected. The question you began with, what is 3I/Atlas doing to Mars, now feels gentler. It is reminding you that planets are not isolated islands. They are participants in a vast, slow exchange that spans stars. And tonight, that thought is enough. Long after 3I/Atlas has slipped beyond the easy reach of Mars orbiters, the real activity begins back on Earth. In conference rooms, simulation labs, and the quiet glow of computer screens running orbital projections at 3 in the morning. Because while Mars itself experienced nothing catastrophic, planetary defense teams treat every unusual object as practice. You might think that an interstellar comet passing millions of kilometers from Mars has little to do with protecting Earth. But in truth, it's an invaluable rehearsal. The Atlas system that first detected 3I/Atlas was built specifically to provide early warnings of near-Earth objects. Since its deployment in the 2010s, Atlas has discovered thousands of asteroids, including several small ones detected just hours before impacting Earth's atmosphere. That's a mainstream success story in planetary defense, catching meter-scale objects before they harmlessly burn up. Interstellar objects, however, add a twist. They move faster. Much faster. Their hyperbolic excess velocities mean they approach the Sun already carrying significant speed. A typical near-Earth asteroid might travel 20 to 30 kilometers per second relative to Earth. An interstellar object can exceed that, sometimes dramatically. Less warning time. Less margin for error. Historians still argue whether current survey systems are sufficient to detect the majority of potentially hazardous objects larger than 1 kilometer, or whether blind spots remain. Particularly for objects approaching from the direction of the Sun. Interstellar bodies complicate this further because they can arrive from almost any direction and at high inclination angles relative to the ecliptic. So when 3I/Atlas was identified, even though it posed no threat, it became a case study. How quickly was it detected after entering observable range? How fast were its orbital parameters constrained? How efficiently did observatories coordinate follow-up measurements? You imagine analysts replaying the timeline. Detection, confirmation, orbit refinement, public announcement. Each step is evaluated. Not dramatically, no red flashing lights, but methodically. Could response times improve? Could automated pipelines flag hyperbolic candidates even faster? There's also the matter of deflection strategies. For solar system asteroids, concepts like kinetic impactors, demonstrated successfully by NASA's DART mission in 2022 when it altered the orbit of the asteroid moonlet Dimorphos, are viable given enough warning time. That was a landmark experiment, proving that we can nudge a small body measurably. But for a fast-moving interstellar object, the window between detection and closest approach could be far shorter. Launching a deflection mission might be impractical unless detection occurs years in advance. Fortunately, the probability of a direct impact from such an object is extraordinarily low. Space is vast. Planets are small. Still, planetary defense doesn't operate on comfort. It operates on preparation. You picture simulation teams modeling hypothetical scenarios. What if an interstellar object on a collision course were detected 6 months before impact? What if only 3 months? Could a kinetic interceptor even reach it in time? Would evacuation be the only option? These are sobering questions, but they remain largely theoretical. A quirky yet serious proposal occasionally surfaces in defense discussions: stationing rapid response interceptors in solar orbit, ready to be redirected toward incoming threats. It sounds like something from science fiction, but the underlying physics is straightforward. The challenge is cost, logistics, and political will, not feasibility. Meanwhile, 3I/Atlas serves as a reminder that our solar system is not closed. Objects can, and do, enter from interstellar space. The Vera C. Rubin Observatory, expected to dramatically increase transient detections, will likely find many more such visitors. Historians still argue whether we've already missed dozens simply because our instruments weren't sensitive enough. Mars' role in this rehearsal is subtle but useful. Observing how an interstellar object behaves near a planet, how dust disperses, how plasma interactions unfold, feeds into broader modeling. Even though Earth was not involved directly in this flyby, the physics is universal. You imagine future generations looking back at 3I/Atlas as part of a growing dataset. First, Oumuamua. Then, Borisov. Now this. Each encounter adds calibration points to detection algorithms and risk assessments. The unknown becomes incrementally familiar. There's something reassuring about that. Fear often thrives in ignorance. But each new interstellar detection chips away at the mystique. They are no longer singular anomalies. They are members of a category. Rare, yes, but classifiable. From Mars' silent surface, none of this administrative choreography is visible. No one there knows that committees are meeting, that white papers are being drafted, that defense models are being refined. The red planet simply continues its orbit. But you, standing in imagination beneath that rust-colored sky, understand the larger implication. 3I/Atlas is not doing anything dramatic to Mars. it is doing something quietly transformative to us. It is forcing humanity to widen its defensive thinking from near-Earth objects to near-solar system objects. It's a subtle shift in perspective, from guarding the neighborhood to acknowledging the highway that runs through it. And highways bring travelers. Most pass harmlessly. Some may one day require action. For now, the rehearsal ends without incident. The object fades. The simulations conclude. Reports are filed. And Mars, untouched, continues its patient rotation, while humanity grows just a little more prepared for whatever might come next from between the stars. Even as 3I/Atlas dwindles into a faint outbound ember, the robotic eyes around Mars refuse to blink. If there is one thing spacecraft do well, it's stare patiently into the dark without complaining about neck strain. You imagine riding along with a Mars reconnaissance orbiter as it slews gently, reaction wheels humming softly, its high-rise camera locking onto a predicted patch of sky. Timing is everything. At interplanetary distances, even a slight miscalculation could leave the object slipping just outside the frame. There are no retakes. HiRISE was designed to image the Martian surface in exquisite detail. Boulders, dunes, rover tracks, but it has occasionally turned outward for calibration and astronomical observations. Capturing 3I/Atlas would not produce a cinematic close-up. At millions of kilometers away, the nucleus remains unresolved, a bright pixel against a black field. But even a pixel has value. Its brightness, its motion relative to background stars, all feed into orbital refinement. Meanwhile, MAVEN continues sampling the upper atmosphere. If any lingering dust from the interstellar visitor filters through, MAVEN's mass spectrometers might catch unusual ion signatures. The changes would be small, barely distinguishable from normal variability, but science thrives on small deviations. You think about how extraordinary it is that machines we built are circling another planet, turning their instruments toward an object born around a different star. A century ago, Mars was still a blurry disk in telescopes. In the late 19th century, astronomer Percival Lowell famously misinterpreted linear surface features as canals, sparking speculation about Martian civilizations. That's a mainstream historical anecdote, an example of how imagination can outrun data. Now, instead of speculating about canals, we're measuring isotopic ratios in an interstellar comet from orbit around Mars. Progress, you might say, has been steady. Historians still argue whether robotic exploration will always precede human footprints on Mars, or whether the two will overlap in coming decades. But for now, robots are our proxies. They do the watching. They collect the photons. They store the bits. You drift lower, down to the surface where Perseverance sits in Jezero crater. Its Mastcam Z system occasionally captures the sky, mostly to monitor dust and clouds. If mission planners scheduled observations during 3I/Atlas' brightest phase, the rover might record a faint moving point across successive frames. Nothing dramatic. No sweeping tail dominating the horizon. Just a tiny, migrating star. Still, imagine the symbolism. A rover tasked with caching rock samples for eventual return to Earth, glancing upward at material from another star system. Mars, once thought possibly inhabited by intelligent beings digging canals, now hosts intelligent machines watching interstellar debris. The irony is almost charming. There's also Mars Odyssey, quietly orbiting since 2001, a veteran spacecraft that has outlived many expectations. It continues mapping minerals and relaying communications. Though not designed for comet observation, its instruments contribute context, background radiation levels, atmospheric conditions during the flyby window. A quirky operational detail: spacecraft must manage their own shadows and thermal constraints carefully. Pointing away from Mars toward deep space can alter temperature balances, requiring careful scheduling. Even interstellar science must respect radiator panels and battery margins. The universe may be grand, but engineering remains practical. As 3I/Atlas recedes, the challenge shifts from brightness to persistence. The farther it travels from the sun, the dimmer it becomes. Outgassing slows as temperatures drop. The coma dissipates. Eventually, it transitions from active comet to inert nucleus once more, a dark, cold body coasting outward. From Mars' orbit, its apparent motion against background stars accelerates slightly as geometry changes. Tracking requires increasingly precise pointing. The object becomes a data point more than a sight. You imagine the final successful image from MRO, a faint speck, catalogued and archived. Engineers nod quietly. Another observation complete. Historians still argue whether future missions should be designed specifically to intercept interstellar objects. Concepts have been proposed: rapid response spacecraft stationed in solar orbit, ready to chase the next visitor. The challenge lies in speed and funding. Interstellar objects do not schedule appointments years in advance. They appear, they pass, they vanish. But perhaps one day, a probe will rendezvous with such a traveler, matching velocity long enough to sample its surface directly. For now, remote sensing must suffice. Back on Mars, dust devils continue tracing lazy spirals across plains. The sky shifts from pale salmon to deeper rust as evening falls. 3I/Atlas is nearly indistinguishable from ordinary stars. And yet, thanks to those orbiting machines, its passage is documented in terabytes of data. Photons captured. Spectra analyzed. Plasma fluctuations logged. Mars itself remains unchanged, no new crater, no atmospheric upheaval, but its orbiters have participated in something rare, observing a piece of another star system in transit. You stand in imagination beside Perseverance as the night grows darker. The rover's instruments power down for the soul, conserving energy. Above, the interstellar wanderer fades beyond unaided vision. The robots have done their part. The data is secured. And 3I/Atlas continues outward, carrying with it nothing from Mars except a minute gravitational nudge, and leaving behind only images, measurements, and the quiet satisfaction that, for a brief time, two distant star systems shared a line of sight. Even as the data settles into archives and spreadsheets, there is always a murmur at the edges of any interstellar discovery. A whisper that asks, not entirely seriously, but not entirely joking either, what if it isn't natural? You've seen this before. In 2017, when Oumuamua displayed that slight, unexplained acceleration without a visible coma, speculation flared. A few scientists proposed the possibility of a light sail, an artificial construct propelled by radiation pressure. Most of the community favored more conventional explanations, such as undetected outgassing of hydrogen. Historians still argue whether the exotic hypothesis deserved as much attention as it received, or whether media amplification distorted a fringe idea into something louder than the evidence warranted. So when 3I/Atlas arrived, behaving mostly like a modest comet, the scientific community watched carefully, but calmly. You imagine the checklist. Is the trajectory consistent with gravitational dynamics? Yes. Is any non-gravitational acceleration explainable by outgassing models? Yes, within uncertainties. Are there unusual periodic signals in reflected light? None detected. Does the spectrum show signatures of manufactured alloys, artificial radio emissions, or structured modulation? No. The absence of evidence is not evidence of absence, as the saying goes, but it is evidence of normalcy. And normalcy, in astronomy, is often far more common than science fiction would prefer. Still, the idea of artificial interstellar probes is not entirely fantasy. Physicists have seriously discussed the possibility of Bracewell probes, hypothetical autonomous spacecraft sent by advanced civilizations to explore the galaxy. The concept dates back to the 1960s. It's speculative, yes, but grounded in physical plausibility. If we can imagine sending robotic probes beyond our solar system in a few centuries, an older civilization might have done so long ago. But speculation requires data. And so far, 3I/Atlas offers none that demand such explanations. Its light curve is irregular but consistent with tumbling rock and ice. Its emissions align with sublimating volatiles. Its motion fits celestial mechanics beautifully. You find something almost comforting in that. The universe is mysterious enough without needing to insert hidden machinery into every anomaly. There's a quirky historical footnote worth remembering. When pulsars were first discovered in 1967, their regular radio pulses were so precise that astronomers briefly labeled the signal LGM-1, little green men. It was a tongue-in-cheek acknowledgement of how unfamiliar phenomena can momentarily seem artificial. Soon enough, neutron stars provided the natural explanation. The lesson lingered: extraordinary claims require extraordinary evidence. With 3I/Atlas, no such extraordinary evidence appears. Still, you indulged the thought experiment for a moment. If it were artificial, what would you expect? Controlled acceleration, course corrections, emissions inconsistent with known chemistry, perhaps structured radio signals embedded in background noise. None of these are observed. The object behaves like every other icy body responding to sunlight and gravity. Historians still argue whether humanity's search for extraterrestrial intelligence should prioritize passive listening, radio telescopes scanning the sky, or active searching for artifacts within our own solar system. Interstellar objects blur that line slightly. They are natural by default, but they pass close enough to study directly. Each one becomes a free sample from elsewhere. You stand beneath the Martian sky and watch the fading speck. There is no blinking beacon. No geometric silhouette unfolding against the stars. Just a dimming point, cooling as it retreats from solar warmth. Perhaps that is the more profound realization. If intelligent life exists elsewhere, and statistically, many scientists suspect it might, the galaxy is vast enough that not every interstellar object needs to be a messenger. Most are simply debris, remnants of planetary formation. Frozen leftovers ejected by gravitational chaos. And yet, even as natural debris, they connect star systems physically. They prove that material exchange occurs without intention. The galaxy does not require spacecraft to share matter. Gravity does it automatically. You smile at the thought that sometimes the mundane explanation is the grand one. A chunk of ice and rock wandering between stars is already astonishing. It does not need antennas. Mars, indifferent to the debate, continues its slow spin. Its ancient surface bears no sign of alien visitation beyond the robots we placed there ourselves. The sky remains clear. As 3I/Atlas dims further, even the fringe whispers quiet. The data holds steady. The models converge. It is what it appears to be, an interstellar comet, shaped by physics, illuminated by our sun, briefly observed from Mars. And maybe that's enough. Because sometimes the most extraordinary truth is that the universe operates consistently. That the same equations apply in distant systems. That rock and ice behave predictably even when born under foreign stars. No secret probe. No hidden message. Just a traveler. And as it slips beyond the threshold of easy detection, you let the speculation fade with it, leaving behind something quieter, steadier, and perhaps even more awe-inspiring, a universe that does not need embellishment to be magnificent. By now, 3I/Atlas is little more than a faint, outbound signature in the most powerful telescopes. For Mars, the encounter is already over. For astronomers, it has just begun to settle into something more enduring. History. You imagine a future classroom, maybe on Earth, maybe one day on Mars itself, where a student scrolls through a timeline of interstellar visitors. 2017, 1I/Oumuamua. 2019, 2I/Borisov. 2020s, 3I/Atlas. What once felt extraordinary begins to look like the early entries of a growing list. That's how normalization happens. The first exoplanet discovered around a sun-like star in 1995 was headline-shattering. Now we catalog thousands. The first image of a black hole seemed almost mythical. Now we refine imaging techniques. The first interstellar object felt like a once-in-a-lifetime anomaly. Now it feels like the beginning of a category. Historians still argue whether scientific revolutions are driven by singular dramatic discoveries or by the slow accumulation of repeated, confirming observations. 3I/Atlas falls into the second group. It does not overturn physics. It reinforces it. You picture future researchers comparing compositional data across multiple interstellar objects. Patterns might emerge. Perhaps most are volatile-rich, suggesting ejection from outer regions of planetary systems. Or maybe a surprising diversity appears, some rocky, some icy, some unusually carbon-heavy. With only 3 confirmed objects so far, conclusions remain tentative. But statistical power grows with numbers. The Vera C. Rubin Observatory, with its enormous field of view and rapid sky survey cadence, is expected to detect far more transient objects. It may reveal that interstellar visitors are not rare at all, just previously unseen. From Mars' perspective, 3I/Atlas will leave no physical memorial, no plaque, no altered terrain. But in orbital databases and spectral archives, it will persist. Its trajectory, slightly bent by Mars' gravity, will be preserved in equations. That tiny deflection will echo across millions of years as it continues through the galaxy. You like that image? Mars quietly signing its name in the curve of a departing object's path. Not with ink, but with gravity. There's a mainstream historical parallel here. When Edmund Halley predicted in 1705 that the comet observed in 1682 would return in 1758, he demonstrated that comets were periodic objects bound by gravity, not random omens. His successful prediction marked a turning point in understanding celestial mechanics. Each subsequent return of Halley's comet reinforced that shift from superstition to science. Similarly, each confirmed interstellar object reinforces the idea that our solar system is permeable. The galaxy is not static. It is dynamic and interconnected. You imagine historians of science writing about this era as the moment humanity first directly sampled material from other star systems, even if only remotely. Before interstellar probes, before warp drives, if such things ever exist, there were these natural emissaries. And you smile at how understated it all is. No grand cosmic handshake. No message in a bottle. Just spectroscopy and orbital mechanics. Mars continues rotating beneath you, its 2 small moons tracing uneven arcs across the sky. Phobos rises in the west and sets in the east, completing an orbit in about 7 hours and 39 minutes, a well-known orbital fact. It appears to race across the sky compared to Earth's moon. Deimos, farther out, moves more slowly. Neither moon reacts to 3I/Atlas. Neither shifts noticeably. The scale difference is immense. Yet in textbooks of the future, perhaps there will be a footnote. During the early 21st century, Mars orbiters participated in observations of the 3rd confirmed interstellar object, 3I/Atlas, during its passage near Mars' orbital distance. A small line, but meaningful. Historians still argue whether humanity's expansion into the solar system will fundamentally alter how we perceive cosmic events. Does witnessing an interstellar object from Mars change its cultural weight? Perhaps. It transforms Mars from passive backdrop to active observing platform. You stand quietly as the object becomes too faint even for imagination. Its light has blended back into the star field. What remains is context. Mars has not been damaged. Not seeded dramatically. Not transformed. It has simply participated in a brief alignment of paths. And in that alignment, humanity has gained practice, data, and perspective. You feel the scale of it all soften. The urgency that accompanied the approach is gone. The questions have shifted from "what is it doing?" to "what have we learned?" The answer is incremental but profound. We have learned that our solar system is not isolated. That objects from other stars pass through, carrying chemistry shaped elsewhere. That Mars can serve as a vantage point in that exchange. And that the galaxy, though vast, is not divided into sealed compartments. 3I/Atlas continues outward, now just another small body coasting through interstellar space. But in your mind, and in the records of science, it has become something more. A marker of an era when humanity began noticing the traffic between the stars. Mars turns. The sun glows steady. And history quietly absorbs another entry. Now that 3I/Atlas is well beyond Mars' immediate neighborhood, your mind drifts to a more improbable question, one that sounds simple but hides layers of orbital complexity. What if it didn't leave? What if, instead of skimming through on a hyperbolic arc, some fragment of it stayed behind? You already know the basic rule. For an object to be captured gravitationally by a planet, it must lose energy. Speed is the enemy of capture. 3I/Atlas arrived with a hyperbolic excess velocity, meaning even far from the Sun, it was moving too fast to be bound. Mars, with only about 11% of Earth's mass, simply does not have the gravitational muscle to grab something barreling past at tens of kilometers per second. That's a mainstream orbital fact. Permanent capture generally requires either a three-body interaction, where energy is exchanged between multiple bodies, or some form of drag. Jupiter, massive and dominant, occasionally captures comets temporarily because its gravity is immense. Mars, by comparison, is more of a polite suggestion than a cosmic net. Historians still argue whether Mars' moons, Phobos and Deimos, were captured asteroids or formed from debris after a large impact. Capture scenarios require complex interactions, possibly involving a thicker ancient Martian atmosphere or tidal fragmentation. The debate remains unresolved. But for 3I/Atlas, permanent capture is extraordinarily unlikely. Still, you let the thought experiment unfold gently. Imagine that during its closest solar approach, outgassing caused a small fragment to break free, perhaps a boulder-sized piece spun off by rotational stress. If that fragment happened to pass close enough to Mars while moving at a slightly lower relative speed, could it be nudged into a bound orbit? In theory, yes. In practice, the probability is vanishingly small. The geometry would need to be exquisite. The velocity difference precise. More likely is temporary capture. Some objects entering a planet's Hill sphere, the region where its gravity dominates over the Sun's, can loop around briefly before escaping again. Mars' Hill sphere extends roughly 1,000,000 kilometers into space. If a tiny fragment wandered into that region at just the right speed, it might orbit once or twice before solar gravity reclaimed it. You picture a faint shard of interstellar ice briefly circling Mars like a hesitant guest, unsure whether to stay. It completes a lopsided loop, then drifts outward again, unable to commit. There's something poetic about that. A near capture. A might-have-been moon. A quirky historical parallel comes to mind. In 2006, astronomers discovered a small object temporarily captured by Earth, an asteroid designated 2006 RH-120, that orbited our planet for about a year before escaping. It wasn't interstellar, but it demonstrated that temporary natural satellites are possible. Earth occasionally hosts these mini-moons. Mars could, in principle, do the same. But with 3I/Atlas, no such capture has been observed. Its path through Mars' orbital distance was too distant, too fast, too clean. The numbers simply don't favor a lingering souvenir. And yet, in a broader sense, something has stayed. The dust dispersed into the interplanetary medium may cross Mars' orbit again long after the nucleus has vanished into deep space. Tiny grains can settle into solar-bound orbits that persist for thousands or millions of years. Some fraction of that dust might intersect Mars' atmosphere in the distant future, long after anyone remembers this specific flyby. Historians still argue whether interplanetary dust contributes meaningfully to planetary surface chemistry over geological timescales. The flux is small but constant. Layer upon layer, atom upon atom, worlds accumulate foreign material. So while Mars has not captured 3I/Atlas in any dramatic way, it may retain a whisper of it, microscopic particles mingled with regolith. Not enough to notice without extraordinary analysis, but enough to say that some trace remains. You look up at Phobos racing across the sky, its irregular shape silhouetted against stars. In a few tens of millions of years, tidal decay will likely cause Phobos to either crash into Mars or break apart into a ring. That's a well-supported prediction based on orbital measurements. Mars' moons are temporary on cosmic timescales. In contrast, 3I/Atlas will not return at all. Its path is open-ended, unbound. Once it leaves the Sun's gravitational well entirely, it becomes a citizen of the galaxy again, orbiting the Milky Way's center over hundreds of millions of years. Capture is intimate. Escape is vast. You feel the difference. Mars could not hold this visitor. It did not have the gravity to keep it close. And perhaps that's fitting. Interstellar objects are, by nature, wanderers. Still, you appreciate the elegance of the question. What if it stayed? What if Mars gained a third moon, born around another star? The idea sounds like science fiction, but it's grounded in orbital mechanics, probabilities, and energy equations. Tonight, though, the outcome is simpler. 3I/Atlas passed through. It bent slightly under Mars' gravity. It may have shed dust that lingers invisibly. But it did not settle into orbit. It did not become a permanent companion. And so Mars remains as it was, 2 small moons, ancient scars, thin air, while the interstellar wanderer continues its solitary path. Some encounters are brief by necessity. And sometimes, that briefness is the whole point. Now that 3I/Atlas is far beyond Mars' orbit, you turn your attention to the quiet aftermath. Not explosions. Not headlines. Just the subtle question, did anything at all change? Mars looks the same. The same rust-colored plains. The same cratered highlands. The same pale sky fading into butterscotch at sunset. If you stood here without knowing the story, you would never guess that material from another star system had just passed nearby. And yet, science rarely looks for dramatic transformations. It looks for residuals. 4 tiny deviations from expectation. MAVEN's atmospheric data is combed for anomalies, slight increases in metallic ions, faint shifts in upper atmospheric chemistry. Nothing dramatic emerges. If any interstellar dust entered the atmosphere, it did so in trace amounts, indistinguishable from the steady drizzle of ordinary micrometeoroids Mars already experiences. That's a mainstream reality. Every planet in the solar system is constantly bombarded by micrometeorites. Earth accumulates tens of thousands of tons of cosmic dust each year. Mars, with its thinner atmosphere and smaller gravitational cross-section, collects less, but still enough to matter over geological time. Against that background flux, 3I/Atlas contributes little. Historians still argue whether cumulative micrometeorite infall significantly alters planetary surface chemistry over billions of years, or whether its contribution is minor compared to volcanic and internal processes. On Mars, where surface processes are slower and erosion is limited, even small inputs might persist longer than on Earth. But teasing out interstellar grains from local ones is extraordinarily difficult. You imagine a future laboratory on Mars, perhaps decades from now, where a returned soil sample is analyzed with exquisite precision. Scientists search for isotopic anomalies, ratios that don't quite match solar system norms. If one grain shows a distinct signature, could it be traced back to a specific interstellar visitor like 3I/Atlas? Probably not directly. Space is messy. Dust streams overlap. Time blurs origins. But the possibility lingers like a faint echo. On the surface, Perseverance continues caching rock cores in titanium tubes, preparing them for eventual return to Earth. Those samples are selected for their potential to preserve ancient biosignatures, not interstellar dust. And yet, embedded within Martian regolith, there may already be pre-solar grains, tiny minerals that predate the Sun. We know such grains exist in meteorites on Earth. It would be surprising if Mars lacked them. So perhaps 3I/Atlas added nothing fundamentally new, only another whisper to a chorus that has been playing for billions of years. You think about the gravitational deflection one more time. Mars nudged the object ever so slightly. That change in trajectory is permanent. Over millions of years, as 3I/Atlas orbits the Milky Way, that tiny bend will compound into a different galactic path than it would have taken otherwise. Mars left a fingerprint, not on its own surface, but on the object's destiny. There's something satisfying about that reversal. We often imagine small bodies affecting planets, impacting, shaping, altering climates. Here, The planet subtly altered the small body instead. A quirky comparison comes to mind. When spacecraft perform gravity assists, they steal a bit of momentum from planets to accelerate. Voyager 2 used Jupiter's gravity to slingshot towards Saturn, Uranus, and Neptune. In doing so, it minutely altered Jupiter's motion, though by an imperceptible amount. Gravity is a two-way interaction, even if one partner barely notices. Mars' influence on 3I/Atlas was tiny but real. A fractional change in velocity. A slight adjustment in outbound direction. Historians still argue whether such minute gravitational interactions across billions of years significantly shape the distribution of small bodies in the galaxy, or whether random stellar encounters dominate their paths. Galactic dynamics is a slow, complex ballet. Each nudge matters, but so do countless others. As for Mars itself, the planet continues losing atmosphere molecule by molecule to the solar wind. Dust storms rise and fall. Polar caps wax and wane with the seasons. If you didn't know about 3I/Atlas, you would see no evidence it ever came. And maybe that's the quiet lesson. Not every cosmic encounter leaves a scar. Not every visitor reshapes the host. Sometimes the universe allows two paths to cross gently, exchange only gravity and photons, and then diverge forever. You stand in the cooling Martian evening, Phobos racing overhead, Deimos hanging more patiently in the distance. The stars sharpen as the sky darkens. Somewhere among them, 3I/Atlas is already too faint to distinguish. It has not transformed Mars. It has not rewritten its geology. It has not seeded forests or carved craters. What it has done is subtler. It has reminded you that Mars exists within a dynamic galaxy, where objects from other star systems can wander close enough to study. It has provided data, practice, perspective. And it has left behind, at most, a dusting of microscopic grains, indistinguishable from the rest, yet born under a different sun. The aftermath, then, is quiet. No headlines etched into rock. No atmospheric glow marking its departure. Just numbers in databases, spectra in archives, and a slight curve in an outbound trajectory. Mars remains Mars. And the wanderer continues on. Now the sky is still. 3I/Atlas has faded beyond even the most patient telescopes circling Mars. Its coma has collapsed as solar warmth weakens. Its tail has thinned into invisibility. What remains is a cold nucleus, coasting outward on a path that will never loop back. You stand on the Martian surface in imagination, boots pressed into dust that has not known rain in billions of years, and you realize the question has quietly answered itself. What is 3I/Atlas doing to Mars? Almost nothing. And almost everything. Physically, Mars is unchanged. No crater marks the encounter. No measurable atmospheric transformation lingers. The planet continues its 687-day orbit around the Sun, turning through sols that last 24 hours and 39 minutes. Phobos still rises in the west. Dust devils still sketch spirals across plains older than complex life on Earth. That's the mainstream, measurable truth. But zoom out, farther than Mars' orbit, farther than the Sun's gravitational reach, and the meaning shifts. 3I/Atlas has demonstrated, once again, that planetary systems are porous. Matter does not stay politely confined to its birthplace. Stars fling debris outward. Gravity scatters fragments into interstellar night. And sometimes, those fragments pass close enough to another world to be studied. Historians still argue whether the galaxy is chemically homogeneous on large scales or whether meaningful regional differences exist between stellar neighborhoods. Each interstellar object adds a data point to that debate. With only a handful observed so far, conclusions remain tentative. But the pattern is emerging: rock, ice, organics, familiar ingredients in unfamiliar combinations. You think about the tiny gravitational nudge Mars imparted. A minute bend in the outbound trajectory. That curve will persist for millions of years as 3I/Atlas orbits the Milky Way's center. Long after Mars' own surface changes, long after Phobos breaks apart or falls, that subtle alteration will still be encoded in the object's path. Mars touched it. Not with atmosphere or impact, but with gravity. There's something beautifully understated about that. In a universe where collisions can vaporize oceans and carve basins thousands of kilometers wide, this encounter was gentle. A near pass. A shared moment in orbital space. You let the scale widen even further. Our Sun itself orbits the Milky Way once every roughly 230 million years. During each galactic year, it weaves through spiral arms, passing near other stars. Over billions of years, countless objects have likely crossed between systems. Most unnoticed, some now detectable because our instruments have improved. A quirky thought drifts through your mind. Somewhere, perhaps tens of thousands of years from now, 3I/Atlas might pass through another young planetary system. If that system hosts observers, they might detect a faint hyperbolic object and trace its incoming direction, back toward a region of space that once contained our Sun. They will not know Mars nudged it. They will not know it skimmed past a rust-colored world with robotic explorers. But the physics will remember. The galaxy is patient that way. You feel your thoughts slowing, lengthening like the object's outbound arc. The urgency of detection, of classification, of speculation has faded. What remains is perspective. Mars was not threatened. It was not transformed. Instead, it served as witness. Witness to a traveler older than its own surface crust. Witness to chemistry forged under alien starlight. Witness to the quiet traffic that moves between suns without ceremony. And you, standing here in imagination, were witness too. The red planet cools into night. The sun slips below the horizon, leaving a blue halo that fades into rust. The stars sharpen. Among them is no sign of 3I/Atlas anymore. It has rejoined the vast anonymity of interstellar space. But the knowledge remains. We now know, directly, observationally, that objects born around other stars can pass near Mars. That they carry familiar chemistry. That they behave according to the same gravitational rules that govern our own comets. That is what 3I/Atlas has done to Mars. It has woven the red planet more tightly into the story of the galaxy. Not through violence. Not through spectacle. Through proximity. Through measurement. Through a shared curve in spacetime. You take one last look at the darkening sky and let the image soften. Mars turning slowly, two small moons circling, the sun glowing steady at the center, and far beyond, a cold fragment from another star drifting outward into endless night. Everything moving. Everything connected. And in that quiet connection, you find the real answer. 3I/Atlas did not change Mars. It reminded you that Mars, and all worlds, are part of something much larger.